let's continue with torsion lection. And in the previous part, we're talking about the angle of twist, and with the assumption that makes more deformation and circular cross section are undistorted, then we have two equations based on the two triangles, two approximate triangle that we draw from the finger due to the torsion on the right side, and that the 2 E5 equal to gamma L over rho, and at the same time gamma equal to 5 rho over L. So with that, we can continue to explore what is the shear strain distribution on the cross section, and also the shear stress distribution on cross section, because it angle of twist, so the torsion it will create this shear stress, and when the shear stress is associated with the shear strain, as you know in lesson 2. So let's continue with the shear strain distribution. Shear strain distribution. From that equation, as you can see, for a given torque, we have with the equation here shear strain, which is gamma for given torque. So gamma equal to 5 rho over L. If given torque, so it known, then you apply on that member the 5, it will be fixed. And then the L, because we assume the circular cross section is undistorted, so the L remain unchanged during the torsion applied on the member. So with that, we can transform the gamma equal to 5 rho over L with following. So for a given torsion or torque, given torque or torsion, we have what? The length of the member and the angle of twist 5 are constant. Angle of twist 5 for constant. So what? So from the equation, gamma above, as you can see, 5 over L rho, 5 over L rho, because L is constant, 5 is constant, so I can name that with a constant K, and in this case I call that K1, and then that K1 over rho. So this component, I make that equal to K1, so that K1 over rho in there. So what does that mean? K5 constant, L constant, so K1, that ratio also constant. So gamma equal to a constant time rho. Rho is changing from the center to the whole radius of the circular cross section. So that you can see that what change in the shear strain, it change depends on the rho. So what we can say from that equation, so basically a linearly linearly proportional between rho and gamma. So from that we can say the shear strain is linearly distributed over the cross section, over cross section, because that is only the function of rho and it linearly distributed. So if rho equals 0, then gamma equals 0 from that equation, as you can see. If rho get to the whole radius, then gamma get the maximum. So from that we can draw the shear strain distribution over the cross section of the material. So if we have the cross section, the center there, and then with that equation, as you can see, Then we have the row chain from 0 from the center to the whole radius, and the gamma is linearly distributed, and it linearly proportional, directly proportional to gamma, to rho. So from that we can have the distribution is 0 in the center, and then rho maximum at rho equal to the center of equal to the radius of the cross section. So let me call the radius of cross section is C. Then we have what? Gamma max. Gamma max. The maximum gamma of the shear strain is at radial distance equal to C, where C is the radius of cross section, circular cross section, and that the only circular solid circular cross section or hollow circular cross section that all we will talking about for torsion in this class. So that is the shear strain distribution. The next one is, as you can see, shear strain, great shear stress, and that the relationship. So let want to talk about the distribution of the shear stress. Here we have the shear stress distribution. From lesson 2, we know chi. Everyone know chi? What is chi? If you're not sure, go to section 2. They call that either modulus of rigidity or the shear modulus. If you're not sure, go back to lesson 2. So it equal to tau, and also at lesson 2 we have it tau within the shear stress over the shear strain gamma. So from that we can have gamma equal to tau over chi, tau over chi. And as you can see, gamma equal to tau over chi. What we can say, 5 at 5 angle of twist equal to gamma L over rho. If I replace gamma equal to T tau over chi, so what do I get from those two equations? Then we can have 5, the angle of twist, equal to tau L over chi. Yo, with the plug of the previous equation to the relationship between the modulus of rigidity, tau shear stress, and gamma shear strain, we can have the angle of twist in that equation. Now let me assume that we assume first homogeneous, so same material throughout homogeneous, and then we also assume isotropic. It means same properties in all direction. Isotropic. And from that, we already know in lesson 2, this 2, we have chi is constant. Chi is constant. From that 2, we have chi constant. So with that, what will we have in terms of the shear distribution? So we will have what? We will have plug in there. So what we have? So we have tau. From that equation, we can have tau. I kick G and rho up and divide L. So what we have is 5G over L times rho from that equation there. So we have that equation. And again, as you can see, 5, we already say if one torsion is applied, then 5 is constant. The length of the member is constant. G, if it assume the material is homogeneous, isotropic, G on constant. So that also 5G over L constant. So let's make that E K2, just similar to here. We make it K1. So make that whole thing is K2 and time rho. And that whole section we set at K2 as we say it in there. So again, you see the similar with the gamma. Gamma equal to K1, a constant rho. We have here tau equal to K2 rho. So from that we can see that for the elastic torsion, we see in the linear portion of the shear stress, shear strain behavior curve. So with that, the shear stress is linearly distributed over cross section. So let we make a similar note in here. The first note that we have, shear strain is linearly distributed over cross section and get maximum at rho equal to C. It's the same here. We can have the for elastic torsion. Then what we have? We have the shear stress is linearly distributed over cross section, over and of course from that we can also have tau max is at rho equals C at above, gamma max at rho equals C. Similarly, tau max also rho over C. So let me box that equation before we go to use the diagram in the book to show you what do we mean like that. Let's box that one. The equation. A note that we need to box. So what does that mean? Let's see the two cross section that we deal with for torsion in this class. As you can see here, the first one is solid circular cross section. The tau, the shear stress is 0 in the center and increasing tau max at rho equal to center, rho equal to the radius of the cross section. For the hollow circular cross section, it's hollow, so at 0 also at the center, but there are no material. So you see using the interpolate, the T minimum is not 0 for hollow cross section, but that at the C1, which is the inner circle, the inner radius, and then we'll get maximum at the outer radius of the hollow cross section. So that is the shear stress distribution, shear strain distribution. So bottom line, the torsion will create the shear stress, and the shear stress distributed 0 to the maximum in the outermost of the circular cross section, regardless of solid circular cross section or hollow cross section. Similarly, the shear strain also get maximum at the outermost of the circular cross section, 0 at the center of the cross section. So with that, we finish with the shear strain distribution and shear stress distribution. In the next part of the lesson, we will talk about the torque and the polar moment of inertia before we apply the worksheet 6A and 6B. And then we also have the torsion in the next lesson that we deal with the statically indeterminate structure. So in this case, apply for the torsion problems.